Hi, everyone. Very nice to have you this week. We are very excited to have Ulrich Habock from Polygon Labs presenting his work on STARKs. Ulrich has been working in the domain of decay for quite a while. He has worked on multivariate lookups, on Fry, on a bit on GKR, on Reed-Solomon cons, and he just published with his co-authors a really interesting report, STARKs. I'm not going to give any spoilers, but it's definitely worth being here today. So thanks a lot to Rich for giving this presentation, and the floor is yours.
Thanks, Raphael. So, as Raphael said, we're going to talk about joint work with David Levitt and Jacha Papini from Starkware, Circle Starks. So, before I start with Circle Starks, let's just go through, let's say, the path that led us in the end to Circle Starks. So, regular Starks. So, I mean, most Starks is what I understand on a regular Stark is just a classical FFT-based Stark. So you have a FFT-friendly field. So it's depicted here as the line, the multiplicative group without the zero. That's smooth, and you have sort of fast encoding, and the objects. So I mean, everybody knows the regular Stark. Your witness data is encoded into univariate polynomial, and then you have the classical polynomial IOP constructions on top of it. So that's what I say, consider a regular Stark. And then there is the elliptic curve Stark, or ECFFT Stark, from Ben Sassen, Dan Carmon, Swastikopati, and David Levitt, which just applies actually to any arbitrarily even non-smooth prime P. So what they do is they just consider a different underlying space of the Stark, not the line or the multiplicative subgroup. You just consider a curved, an elliptic curve as the basis, considering that this elliptic curve in group structure is sufficiently smooth. You place your tray, you choose your smooth subgroup of the curve, you place your data on it, and encode into, well, in this case, it's not polynomials. There are more rational functions here over that curve. So the thing is, at least from my team, and I also saw other team, that there seems to be a misconception about the ECFFT Stark. So it's as efficient, so you can run it over any P in terms of operations, even from the way that the FFT works is as efficient as a classical regular Stark. It just unlocks for any P. The problem with, maybe that's the reason why there is some misconceptions about the EC Stark in the CK community. They're huge 80 pages. It's very complicated to go through them. I personally have to admit, didn't do it yet in all details. So the thing is always like, can we do a simpler construction? And that leads us exactly to the circle. So the point is, a circle Stark is exactly, it's like pulling over the strategy we have over the elliptic curve over a much simpler curve, and that's the unit circle. So the unit circle, so the unit circle was already used back then by, if I remember correctly, by the Mersenne Reed-Solomon codes over a circle group paper by Daniel, Jackie, and me. And this construction was already quite simple, but it has some caveats. So the point of the circle Stark is to have really direct translation of the ECFFT Stark to a much simpler curve, a curve that everybody can understand because it's a quadratic curve. It's the unit circle. It's a group, as you can see. So the unit is here. You just have an angular addition, or if you want to consider it in the spirit of complex numbers, you just multiply complex numbers of the unit circle. That's the group law here. And the reason for why this curve is interesting is the P+1 smooth case is interesting is that it applies to the Mersenne 31, which is probably amongst this prime fields one of the best choices for efficient arithmetics on standard CPU architectures. Okay, so that's the circle Stark, and how it's built. It's like a regular Stark. So actually, there's not so much different on high level. You could say it's the same. You know, you have your circle. You place the circle turns out to be smooth. You place your trace domain essentially as a subgroup of the circle. Then you use the circle FFT, which I will discuss in more detail later, to encode this data you place on the trace columns into. And again, that's the nice thing, and that's the difference to the elliptic curve situation. Now, what you obtain are polynomials again. They're bivariate, and they're over the circle that's depicted here. I cannot highlight on this slide. Sorry. This is depicted here by the relation given by the circuit. So x squared plus y squared is 1. So you encode the trace columns into bivariate polynomials. And yeah, then the usual IOP construction. So you can Schwarz-Zippel. So you sample a random point. The underlying variety is the circle curve. You sample a random point and test your polynomial identities at that random point. For soundness, of course, you typically need to move over to that curve that over an extension field instead of over the base field. But that's not a problem here. So okay. So the main ingredients, as already indicated, are circle FFT, that's needed for efficient encoding, for efficient polynomial arithmetics. And the second thing, and very much related, because typically if you have one concept like in a fast encoder, fast FFT tree, so to speak, then it's also clear how to build from it a low degree test, which is circle free in this situation. So because they're so much related, and I would say the core or most important construction is the FFT anyway, I will now focus only on the circle FFT. So just to recall the picture, we have the circle, we have some smooth subgroup over it, place some data on it, and now we want to have a fast interpolation by bivariate polynomials. Okay, so first of all, and that's probably one of the subtle things, at least for me, that was when I was approaching circle FFT, because I'm coming rather from the classical FFT theory, so harmonic FFTs. So it's an algebraic FFT, like the additive FFT that works on subspaces over binary fields. And so it's not an harmonic FFT. Nevertheless, the way it's built is relies very much on the group structure of the underlying domain. And so I will come back to that later. And there's another thing which makes it actually quite different to the additive FFT. The additive FFT can be seen, the general construction. I'm just now hand wavy because I can't edit on the slide. So typically the short story is you just need a chain of 2-to-1 projections, 2-to-1 mappings. You start with a first domain and you have a 2-to-1 mapping to a domain half the size and so on. And on top of it, you just need something that distinguishes points along the fibers. Once you have it, and the whole additive FFT can be seen as this construction, then you can bootstrap an FFT algorithm from it. Difference of the circle FFT and the ECFFT is that it's just these 2-to-1 mappings are not they're more subtle to be constructed. So maybe better if I rewind here. This was already far too complicated to expect. So let's go back and consider the classical regular FFT. You can consider it as the odd and even decomposition FFT. So that the main core element of it is that you have the group doubling map, or or the squaring map in the multiplicative lingo, which lets the trace to start with the subgroup collapse to one of half the size. And then again, a collapse of one of quarter the size. So that's the same also for the circle FFT, but you need to work not just with the group squaring map, this endomorphism, also with another endomorphism, which is not 2 to 1 in its proper. It doesn't collapse. So okay, so that's the main difference. Algebraic FFT, it's nevertheless it uses a lot of group structure behind it, and it works with 2 endomorphisms: the group squaring and the inverse map. These 2 commute actually because both are power maps. And the domains you choose here, they're what we call standard position cosets. So that are these are cosets of the subgroup which are invariant under the inverse map. Moreover, there's no fixed point. You could also choose the group itself, the group position itself, as something that is invariant, but then you would have exactly the 2 fixed points of the inverse map, which is like the identity element where the cursor is now and its opposite point on the circle. So that wouldn't be a standard position coset. So standard position coset, you have exactly this picture. So each of these involution orbits consists of 2 points. Or in other words, if you consider the quotient space by the action of the involution, you get here something that consists exactly of half the points. Okay, so we have exactly 1, 2, 3, 4 different orbits instead of 8 points of the initial domains. Okay, so and already hand wavy indicated the general principle. You have typically for algebraic FFTs, you have a chain of 2 to 1 maps. So here the chain goes as follows. So you start with your initial standard position coset, and then you consider its quotient with respect to the inverse map, which is exactly of half the size points. And the funny thing is because quotient, because the group doubling map, the endomorphism and the inverse map, they commute. Therefore, you have a unique understanding, a unique definition of the group doubling also on the quotient here. So that's the same. I misused the same P for though here above it's the group doubling. Here it's something like the projection of the group doubling onto the quotient. So, but and yeah, so now you first consider the quotient space half the size, and then repeatedly apply the group doubling map, which again halves these quotient spaces until you end up with a triple space. So that's essentially chain of 2 to 1 maps to get here. So and what you do is like the classical general concept. You decompose into odd and even function with respect in a proper notion, similar like we are used to. So let me try to explain that a bit better here. So given this standard position coset here, yeah. So the first step is actually, you can consider, because that already was indicated in the picture before, that you can consider a model of the quotient space with respect to the involution being on the x-axis itself. So in the first step, you decompose the function into odd and even with respect to the involution. What's odd? What's even? It's better to start. It's invariant with respect to involution. So you take the even part of f, which is f of xy plus f at some point, and its involuted point, its inverse point half. That's invariant under the involution because you took the average over the orbit. And for the odd part, you just take the difference. And then if you take as your standard representative odd function the function y itself, you again get because this is odd, this alternates under the action of the involution, y also alternates, so this quotient is again something that is constant over orbits of the involution. And so in other words, it only depends on x. So the first step, you just you actually decompose the p-variate polynomial, or let's say you would decompose a p-variate polynomial in two univariate polynomials, f0 of x and f1 of x. Okay, and the other steps, they are quite with respect to the group doubling map on the quotient space. So, and group doubling on the quotient space actually reads like this. It's the 2x squared times -1. So it's easy to see that. So I'm not going through it. So and that means, again, group doubling plus, like in the non-projected domains, P and its opposite points, they are really mapped to the same value. Here it's like x and -x, we are mapped to the same value still, you know. And what you do is, again, you decompose into an even part here. This is even with respect to the root, with respect to multiplication by -1, which really maps one point to its partner in the fiber with the same value, and here in an odd one. And x itself is also alternating. It's odd with respect to with the plus-minus map here. So you just take the quotient of it. So the decomposition is very much the same as we are used to in the regular FFT, in the multiplicative FFT. It's just a bit more different here, that it's not x squared that you have here as the projection mapping. So these are the other steps. So essentially, it's very close to the regular FFT. And the point is, in code, it's really essentially the same, one could say. It's a bit too simplified, but you can really do an in-place modification butterfly network that is very, very similar to Cooley-Tukey. In terms of arithmetic costs, it's the same like in regular FFT, and there are some extra technicalities, because in STARKs one often likes to have a coset FFT also. Circle FFT is restricted to standard position cosets. So what would be the other coset? I mean, there are possibilities to extrapolate to other cosets and to maintain the usual way of thinking here, like we used to in regular STARKs, but it's more efficient. From point of efficiency, the better choice is here to generalize from standard position coset domains to something which is here, the left here, to something which is then a twin coset domain. So twin coset domain are now two orbits or two subgroups of half the size. Nevertheless, one is mapped to they're mapped on one onto each other by the involution, by the inverse map, you know. So you can see a standard position coset also as a special case of a twin coset. Here we have the two cosets half the size. The blue coset is mapped on the red coset under involution. But more generally, you can now break the groups, the large group structure. And it can be shown. So the point is, what I want to say here is, there is an analog of the coset FFT. It's a bit more abstract in the way domains look like. In practice, when you write everything down in code, it's very much very similar, because it's all just about how you index the domains. So okay, so circle FFT, essentially like the regular FFT, there are some technicalities about the indexing to get a generalized coset FFT. Okay, Oh, these are quite old benchmarks. I would have needed to ask Schacher. He already optimized his FFT for the Stu proof for Stark prover. We at Polygon are a bit slower in development here, so we don't have yet really optimized the circle FFT. But this was from back then. So typically one would expect this. So Baby Bear is a quite cool 32-bit prime over which you can run all the classical regular Starks. So M31 is just faster in field arithmetics, and it depends a little bit on which CPU architecture you take. So you see. So here we've taken Intel, and if you consider AVX2 a vector instruction set, there you essentially see the same ratio of improvement you see on the multiplication. So that's just a rough picture here what to expect, and I think maybe Schacher did even improve on that, not sure, but that's something what to expect. So you unlock M31 which is per se not FFT friendly, to do the whole Stark over it. You enjoy the benefits of M31. It's not like you enter a different league. Baby Bear Stark is fast, but this Stark is like at least, FFT is like 1.4 larger. The whole trace computations, whenever you use multiplication, you're like 1.4 faster. So it should pay off in the end, in particular if you use hash function for commit, which are arithmetic ones. Not a different league, yet still an improvement you want to have, in particular, given the fact that the implementation of the circle Stark, it's not like a completely different paradigm in the way the code structure looks like than a regular Stark. Okay, so not sure if this quick going over it was a bit too fast and helped something. So there are a lot of details I was just not mentioning. So if you're interested, the paper itself, I hope it's readable. At least for me, it is much simpler than the ECFFT because you don't need any algebraic geometry. That's the fine thing. So you understand the circle. You can even learn terms of algebraic geometry. It can be even, for me, was like a learning step towards ECFFT, understanding the ECFFT, because the circle is very easy to understand, not like an elliptic curve. And even you can practice all the notions, the elementary notions of algebraic geometry on that circle much easier, as an exercise. Okay, so that was it, probably a bit faster than expected.
Thanks a lot, Ulrich, for this presentation. I don't see any questions yet on the chat, so I will ask a couple. And if anyone wants, please feel free to ask after me. So in the benchmark that you just showed, it was single threading. And so you say that you had better benchmarks and more recent benchmarks recently. I was just wondering, because you're saying that the CFFT algorithm is close to Color-TK, whether there's... Sorry, I wanted to confirm rather than ask, actually, that you can parallelize this algorithm, and so you could have much better results to begin with.
Yeah, I mean, Schacher has already implemented a memory-efficient, a cache-friendly version of it, so that it just didn't have it back then time. So the timings we have in the appendix of the Circle Stark paper back then, these timings were just that they show, for versus Baby Bear in the multi-threaded setting, they were equal because memory in both implementation that we used to compare, they were both memory bottleneck. So, but it's absolutely no problem. It's very much the same structure you have even in the in-place modification butterfly networks. So you can make it cache friendly. Yeah, and you see the similar. Then you see again M31, the benefit of M31 over Baby Bear.
Yeah. My other question was actually a bit about M31.
Mhm.
So in SNARK and STARK recently, we've seen convergence in research for using smaller and smaller fields.
Mhm.
And so circle stack is contributing to that. Do you think that do you think that Mersenne prime is going to be the field that everyone is going to converge to? Why I'm saying that is because being part of a couple of projects, um, I can see that changing of protocol, changing of prime is a discussion that often happens, but it's quite difficult for engineers because it means that you have to change a big chunk of your backend, you have to re-optimize everything, and seeing so many papers going through small primes, it could be a, a god bless. It could be great for the engineering for crypto engineers, uh, for maintenance, but also for the evolution of the ZK stack.
Yeah, I'm probably one wrong person to ask here, because as I understood, because there are also smaller Mersenne primes, just as an
Yeah.
example. I'm returning to the completely different approach by Ule Tanner in a second. But if it's just about prime field STARKs, they're smaller prime Mersenne primes, also like M17. It's more really, I think it very much depends on the platform you want to optimize for. It seems like at least on standard CPU architectures like Apple M1 as well. I'm not even sure if I named the right thing here, and Intel, on CPU architectures, and possibly a lot of it also carries over to GPUs. Seems like these M31 seems somehow to be a sweet spot, to hit the sweet spot here. So M17 arithmetic, as I understood by our engineers, wouldn't be better. So even though you would have less embedding overhead. So don't know where the future will move. There maybe it will in small primes, maybe we will stop with baby bear M31 here in prime field. The question is how fast in the end binary provers will be on standard CPU architectures, because on hardware, given that everything is on chip, binary circuits are superior.
Mm.
That's a clear-cut thing. When it comes to FPGAs, I think the answer is not that easy as I understood to give here. So will be very interesting. So I'm very excited of the work also of like revisiting binary feed STARKs, having zero embedding overhead, which is the unique, let's say the unique feature that the Ulitana guys brought into binary STARK. So that's I'm quite excited. So don't know on software which one will be better.
Yeah.
I really can't say. So we will see here. And about engineering, my feeling is for standardization, probably it's a too much vivid field. It's probably far too early to hope for standardization, and therefore helping the developers not to go through the same process again and again.
I agree with you, and thanks a lot for your insights. I worked in the past on ZK rollups. I'm working on ZK VM, and while before problems were mostly the main problem was having a fast verifier. Recently, for the past year or two, I think most people have been working on fast provers and memory efficient provers, and so there are two main themes, at least in my mind, that I can why I see the research conversion, which is the use of small prime fields, and trying to abandon FFTs for SNARKs because they are polylog and they are and login.
Mm.
And yeah, because STARKs have been using small field for longer, I thought that it could be interesting to have some insight on this question. But I agree with you. Standardization it's not there yet. So it's quite an dangerous game to predict what's going to happen in the future. I don't know much about the Stark space, but I know that on the Stark space is the ZK proof organization, which is trying to standardize. I think they started the process about a year ago, and uh, it is difficult because you want to standardize quite different things, and the research is evolving so quickly that you have to always adapt your model to take the new optimizations and new schemes into account.
Mm,
So yeah, I agree with you. And thanks a lot for answering our questions. Um,
you're welcome.
so uh, I'll give some moments in case anyone wants to ask another questions. Otherwise, I think that we can leave.
Hello, I have a question.
Perfect.
Hello, sir. Thank you for the presentation. My name is Logan. I'm a third year computer science student, and I'm looking into trying to implement this. And I was curious what your thoughts are on the biggest differences between circle Stark and normal Stark in terms of writing FRI or FRI for circle
Mhm.
Stark.
Better question would be the better question for who really did implement it, like Elia from our team and Shachar and others from StarkWeb. But my feeling is that the most subtle thing you have to grok here is the indexing of twin coset domains, because the right indexing also of which covers also the right indexing for what they call standard position coset. Fry itself goes very much, well, once you have the indexing, it looks very much the same. Not saying it is exactly the same, because in the end you have still, you know, like with the circle FFT, and therefore also circle Fry. So the first step is like for Fry would be a combination down to domains which are over X alone, and then you do something quite similar as you're used to. So I think in implementing let's say the biggest effort to be done is understanding the circle FFT, getting the circle FFT code done. Once you understood the circle FFT code, you understand also how to do Fry, and the rest is essentially quite the same. A bit more problematic when it comes, let's say, a bit, you have to think in every single detail, you know. The whole Stark is about much more than just encoding polynomials and doing Fry. It's like succinct selector polynomials for the air, or even the deep single point quotients. They're like extra, though it's a simpler curve, you have to spend some extra thoughts about how you do single point quotients, the deep quotients, which you probably wouldn't over the elliptic curve. But I'm talking too much, so long story short, I would recommend study the ECFFT, understand the ECFFT, and then you have 80% up to 90%. You know what to change in the what to do in the implementation. Second thing is selector polynomials are a little bit more different, and the deep quotient itself.
Got it. Thank you.
You're welcome.
Well, thanks again, Ulrich, for this presentation, and thanks everyone for attending. I hope that you had a good time and that everyone's going to have a look through the papers. Thanks again, Ulrich, for coming, and have a good day, everyone.
Thanks for having me.